President and managers, we have John Breitens. He's the lead scientist with Claros Technologies, and we have a short presentation. You may recall at the last board meeting, I introduced some of the work that they're doing and discussed in the initial meeting that we had. Since then, several of their staff met with myself and a couple of our engineers to look at some sites and also consider this as a future technology for the purpose of phosphorus removal, not only within the Forest Lake, but also at a much broader level. So, thank you, John.
Thanks, Mike. Can everyone hear me okay? Yeah. Perfect. So as Mike said, I'm the lead scientist of Claros Technologies. My name is John Breitens. Claros Technologies is a new startup coming out of the University of Minnesota with the mission to use the latest advancements in science and engineering to develop solutions for natural resources. The reason I highlight science and engineering is that we are a research-based company. We are a science-based company. That means, A, you will see a lot of the graphs in this presentation. B, that means we are looking for evidence-based solutions. We want solutions that will work and solutions that we can monitor, track, and eventually prove that they will work, especially in field conditions. This might be old news for a lot of you attending this meeting, but phosphorus presents many issues in freshwater systems. Phosphorus is a main driver of eutrophication and of algae blooms. And as algae grows, it can deplete oxygen in water to the tune of killing off fishing industries and resulting in tourism losses to the tune of $38 million a year and tourism losses in $47 million. Additionally, phosphorus is a limited mined resource, and the global demand for phosphorus is projected to increase for anywhere from 50 to 100% by 2050. So phosphorus is entering into our lake water, it's entering into our rivers and into the ocean, and what we really need to do is we need to find a way to capture it, harvest it, and recover it. Current technologies suffer from various limitations. Those technologies include chemical precipitation, ion exchange, biological methods, and absorption. The main limitation is that they have low removal capacity. What this means is that they don't take out very much and they don't do it very quickly. They're also dependent on various medium conditions, such as pH, dissolved oxygen, things like that. They have high capital investments and they take up a large footprint. Furthermore, no technology has reached the ability to remove phosphorus down below 10 parts per billion. The reason that value is important is because 10 parts per billion is the level needed to stimulate algae growth in a lake water. So at Claros, we develop novel solutions, and one of our solutions is using nanotechnology to capture phosphorus. The photos that I'm showing here are two different formulated sorbents. We take materials and we are able to use our patented process to grow nanoparticles on them. On the left, you will see a granular sorbent material, and on the right, you will see a porous foam support. Why do we use nanotechnology? So nanoparticles are things that are very, 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 very small. For some perspective, your fingernail is 100,000 nanometers thick, and your fingernails also grow 1 nanometer every second. Why do we want to use these? Because they are very small. They're also very reactive. So if you look on the picture on the right, we have millions of these tiny particles embedded within this material. Each one of these particles can capture an atom of phosphorus. That means that we can capture a lot of phosphorus very quickly and ultimately in a very small footprint, which I will demonstrate throughout the course of this talk. One of the first limitations of some of the conventional technologies that I mentioned is that they are not able to operate very quickly. Here we show a graph that we can achieve over 94% capture of our phosphorus in a few seconds. And we can also remove phosphorus to undetectable levels, also within a few seconds. I should note that this is all dissolved phosphorus. We are just targeting dissolved orthophosphate. And what does this mean in a field application? That means we can put our solution into the field and only have short residence times. It means we do not need to have a lot of flow control. It means we do not have a lot of backlog and a lot of stoppage of flow, which is very important for lands next to residences that we don't want to flood.
Would you just define for the audience dissolved phosphorus? What
Yes.
that means?
So phosphorus exists in various forms in the environment. You have solid-bound phosphorus, and the solid-bound phosphorus is phosphorus that is attached to sediment particles, sand, things like that. These sediments will travel through ditches and ultimately into the lakes. But the best way of getting rid of sediment-bound phosphorus is to just remove the solids. So any sort of management practice like a wetland will remove that solid-bound phosphorus. However, the dissolved phosphorus is phosphorus that is not attached to these sediments. It is released from these sediments, and it is free to move in the water. So it is much more mobile, and it's also much harder to get at with conventional management practices. Thank you for the question. The other large advantage of our technology is the loading capacity. So loading capacity we define as the amount of phosphorus that can be captured per milligram of our sorbent material. So we report a loading capacity of above or near 700 milligrams of phosphorus per gram. To put that in perspective, that's loading capacity is 10 times higher, with current formulations up to 30 times higher than conventional materials that are used right now to capture phosphorus. Again, what does this mean for a field application? This means that we can capture a lot of phosphorus in a very small area. Next, here is a graph showing some of the samples that we procured from a local lake in St. Paul, where we are based. And what you can see here is we see common nutrients found in lake waters, boron, calcium, potassium, other things like that. And on the far right-hand side, we don't see a red bar because we have captured all of the phosphorus. We've brought the phosphorus down to undetectable levels without taking out some of these essential nutrients from the water. This shows that we are selective towards phosphorus, and that the water quality will not be compromised by the addition of our sorbent. And this is a proof of concept. We have 2 vials here. One vial, we added 1.5 milligrams per liter of phosphorus. We added phosphorus to both of these vials. We treated one of them, and then we cultured a strain of algae in them. And so as you can see, the water that has been treated with our sorbent material, there's not enough phosphorus left to grow that algae, as compared to our untreated vial on the right, which has a live culture in it. So we're here today. We met with Mike and Megan to establish a partnership with Forest Lake. And the shared objective between Forest Lake and Claros is to obtain data and demonstrate the effectiveness of the material. We're not here to sell you anything. We are a very new startup company, and we really want to, A, have an impact in our community, B, we want to demonstrate that we can apply these sorbents in the field. We've worked with some industrial partners in stormwater and in chemical manufacturing, but we really want to know if we can apply this in a field scenario outside in the nitty-gritty. And the main objective is our new technology. We want to benefit Forest Lake by putting in, having superior removal compared to what the watershed uses right now, and with a smaller footprint and a lower cost. So just touching on our first proposed project site. Our first proposed project site is an area off of Hayward Avenue. There is a small drainage ditch that goes directly into Forest Lake and a culvert that goes under Hayward Avenue. We estimate that we need about 1/2 cubic yard to put into this culvert in order to capture all of the dissolved phosphorus. These estimates were made from data provided by Megan from EOR. And so what we anticipate, about 1/2 cubic yard is about, I imagine the whole system would be about the size of a refrigerator. And so putting in a system like that into these culverts is key. Mike was very helpful in identifying some of these areas for us, looking at areas that had relatively intermediate flows, but also areas that did not have a lot of sediments in the water. That is one of the biggest drawbacks of our material. When you put in a filter material, you do not want it to be clogged with sediments. So this area, as well as the other proposed site, is at the end of a wetland. So we believe that the wetland will remove a lot of the solid fraction from the water, and that we can successfully deploy our material in this area. Furthermore, because of the low footprint, we should be able to utilize all lands on the easements. Now, we should not have to intrude on any private property. Next, the next proposed site is along the Sunrise River. This is a culvert that goes under a regional bike trail and under Highway 61. We estimate that we need about 1 cubic yard, so about a refrigerator and a half for this entire system. And we need that to remove all of the dissolved phosphorus that is found based on data from 2016 provided by Megan. So the purpose of this presentation was to introduce ourselves to the community, introduce ourselves to the board, and we would like this partnership to continue, especially with Mike and his team. And we will continue to optimize design and design the implementation systems and evaluate total project costs from not just from a material standpoint, but from an engineering and monitoring side as well. And upon finalization of the project plan, we will be back to talk to the board, and we'd like to continue a relationship both with the district and with the community. And at the same time, we will be using our updated figures and updated cost estimates to apply for external funding. We've identified 2 sources from the Legislative Commission and another source from the Pollution Control Agency, and we will keep an eye out for other sources as they come along that we can apply in conjunction with the Watershed District. Thank you. I would like to take this time to acknowledge some of the other workers in the laboratory at the University of Minnesota who contributed to this research, namely Fatma Haidari and Jack Anderson. And with that, I will take any questions from the board and from the community. Thank you.
I think before we do that, if Mike, maybe you can just talk a little bit on page 2 about the 2 sites and the phosphorus that we're expecting to see captured on both sites. And then just clarify on the Sunrise River project site, is that the ditch that comes out from Himes Lake, or is that the one coming out of the city of Forest Lake?
Madam President, managers. Yes, so the 2 sites, what we were looking for was ideally, first of all, an area that was already under some sort of public control, either within a right-of-way or otherwise. So we were trying to look at that, and then in addition to the monitoring data that we have of areas of interest for the district based on our diagnostic monitoring over the last several years. And so we looked at several sites in person. So, and of course, John and his team would have a better idea as to what would be the potential better application. But Dr. Funke had provided a lot of the flow data along with the concentration, which was important to understand like what would be some optimal things for field deployment of this technology. So that was how we came to the Hayward Avenue site, just sort of given the drainage area. For the other site, as noted, Sunrise River, that is the drainage area from Bixby Park. And then that culvert there is between the bike trail. Well, there's a road there, and then the bike trail, and then Highway 61. So what we would propose is the public right-of-way area between the road and the bike trail. And again, part of it is then that we can deploy from the right-of-ways or the access, and that would be fairly easy to monitor and also make sure that there's not anything maybe obstructing or being able to get in and clean if we have to. But a lot of those questions still have to be figured out on the design side.
Mm-hmm. So. And then just to call out for the audience, the Hayward Avenue site contributes 50 pounds of dissolved phosphorus in summer months to Forest Lake. And the site along the Sunrise going to Comfort, the range is estimated 500 to 900 pounds per year. And so this installation is estimated to absorb 500 pounds at the low end. So that's very significant. 1 pound of phosphorus generates is it 500 pounds of algae? Yeah, so it's really significant. Very exciting.
Thank you.